So we're going to start off with a little question here. Okay, what is this picture on the left? And what is that picture on the right? The dog. Wow, you guys have amazingly good, eyesight. So what if I were to ask you now? Still, cat and a dog?
Dog is clearer.
Yeah, I guess, would you guess that that's a cat?
No, I don't think that's a I think it's a video game.
Yeah.
Maybe from podcast.
Uh,
Oh, now yeah.
yeah, okay, and so different type of image. Okay, and so your original images are here, and I, put some, filters or whatnot. Okay, how about this thing here? What does this look like to you?
Oh, not Totoro.
A Totoro? Yeah?
I think so. It kind of looks like a cherry blossom with some name in the middle.
Okay. Cherry blossom. Okay, so what about, so I'm gonna give you the same image, different filter.
Oh, I see it now.
You see? Okay, yeah, oh yeah, the cat is there now, and the original image is over here. So there's this kind of interesting, oh yeah, go
What's
ahead.
that filter on the first? Like, what's it mean?
We're gonna talk all about filters today.
Okay.
Yeah, so we'll get into that in a second. But I think the kind of point here is that you don't actually need the original image, right? You could actually, if I were to do some kind of classification test, right, I can actually get by with a lot less detail, right? There's something about this image that our brains are latching onto, right, that lets us do this kind of identification process. And the question is, why wouldn't a like some kind of regression tool be able to do something similar, right? And so what we're going to talk about today is convolutional neural networks. It's an application of stuff and building on the foundation of the basics that we learned about last time, and thinking specifically about how to filter things and pass information that lets us scale down the information, right? Because if I think about like this particular picture as information that gets passed into some kind of processor, right? Every pixel contains data. I mean, the resolution of this picture is going to be pretty large, right? You're actually talking about, if I'm on a 1028 or 1024 by 1024 image, you are literally passing 1,000,000 points of information times 3 actually, because you have colors, right? And so we're going to think about how we can actually translate image information into something that's more digestible for these machine learning tools. Okay, so today is kind of a little bit of a departure. We're going to try and do something a little bit different from typical. Okay, so jumping on over to our iPad. And then for the last half of class, I'm going to do kind of a broader overview of everything that we've talked about so far. All right. Oh, and I need to... Okay, so we are on lecture 17, I believe. And so this will be our last lecture before we do our presentations next week. So convolutional neural networks. This is a class of deep neural networks. Right, and when we're talking about deep neural networks, right, that is kind of referring to the number of layers. So this is a regularized version of a multi-layer perceptron. So these are particularly suited to analyzing grids. So grids of data, such as images, especially for classification. You might do like spatial stuff as well, right? Because those operate in grids as well. So if I were to take a picture, so consider, let's say, a picture of, we'll do something like this. Okay, here's my little bird over here. So as I was kind of just describing, the way that this gets decomposed into like numerical data for the purposes of passing it into some kind of model is we basically define this into grids, right? And you're actually going to have several of these. And these will correspond to each pixel will have some number associated with it for our red, green, blue, right? So has everyone heard of RGB? Yeah, and so the combination of red, green, blues, I'm trying to remember, because they use a different trio for whether it's in digital versus print, but CMY is for print, yeah. But for digital, we use red, green, blue. And the combination of these three colors let us essentially define the full sort of color spectrum, right? And then each value, I believe, is out of 255, right? And so you can go anywhere from, is it 0 or 1 to 255? Yeah, and so you essentially from this picture get this big matrix of values, right? And it's 3 times the number of pixels, 1 for each color filter. And so that is too many weights for a multi-layer perceptron. But it turns out, you don't need to actually pass all of that information. And so we're going to process these images with a couple of different techniques in order to prepare it for use in a neural network processing. So we will process images with 3 techniques. So the first one is the convolutional layer. Second one is the pooling layer. This is the convolutional process. And then our fully connected layer. Okay, any questions so far?
Sorry. This method is just useful for classifications, or can you use this for other?
No, you can use it for other things. I guess the like quintessential examples of CNNs are usually applied for classifications, but they don't have to be. Yeah. Okay, so let's take a look at a example. So let's suppose I've got a matrix, a 5x5 matrix that looks like this. All right, I'm just gonna write down some values here. And so these are kind of values that you might see in one of your color matrices corresponding to an image. This is all kind of just made up numbers, so this isn't actually like an image of anything, but we'll see why we need this in just a second. So what I'm going to do, so we're going to talk about something called stride, which is the number of steps in a direction that we can apply our filter to. And so I'm going to apply a 3x3 filter that looks like this. So this is a filter of stride 3. It moves 3 steps in each direction. And I'm going to write a couple values down here, and we'll talk about where these come from in just a second. Okay. So, does anyone know where this 41.6 might come from?
Top corner.
Yeah, that's right. So, this blue box that I just drew around this kind of first 3x3 corner, that corresponds to this. So 41.6 is actually the average value of those nine elements. Okay, and so this particular filter is called a mean blur filter or kernel. Okay? And so what this has done is our image has taken a bunch of pixels and collapsed them to be an average value, right? So you can imagine if, you know, those guys are like browns over there, it's now kind of the average brown of, you know, those 9 values. So image is now smaller, right? We've gone from a 5 by 5 down to a 3 by 3, and it's now also blurrier, right? But the blurrier may not actually be a problem, as you guys were still able to identify a really blurry cat and dog, right? Okay, and we can actually, so there are some techniques. This can be alleviated by padding, and that helps with the blurriness. But yes, okay, so this is one particular type of filter that will help reduce the size a lot. Okay, so other types of filters. Or actually, I'll stop there and ask if there's any questions so far about any of this. Okay. So oh yes.
So like, using the mean, like the filter to get a subset,
Yep.
like the kernel, but like, those values don't mean anything right away, right? Because they has to be learned in the model.
Yeah.
Yeah.
So right now what we're talking about is this idea that like images tend to be very, very information dense to the point that you don't need all of that information if you wanted to do some kind of classification problem. And because it can actually be a little bit burdensome or computationally complex to try and process all that information, what we are talking about right now are common techniques that you would use to pre-process things before you pass them into your convolutional neural network. Although a lot of people kind of consider this thing that we're talking about here as like fundamentally part of the process of doing your convolution. Yeah. So other types of filters, we have edge filters. So I'll show a couple examples of edge filters. 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1. So this is a vertical edge filter. And you can probably guess that we also have a horizontal edge filter, like so. There's something called a Sobel filter. 1, 2, 1, 0, 0, 0, negative 1, negative 2, negative 1. And even more extreme, there's a Shar filter. 3, 10, 3, 0, negative 3, negative 10. 3. Okay, and so how do these work? So imagine that we've got some kind of matrix that looks like this. So this will be a 6 by 6. Okay, and I'll just make up some values. Let's say we have something that looks like this. Okay, so who can tell me what this matrix would look like as a picture? Yeah, so you'd have one color on one side, right? So, you might have, yeah, so you have a color here, and then you would have a different color over here, right? They're all one value. Okay, and so if I were to apply a vertical filter to this, you would see that this would then become something like this. This would transform into a 4x4, and we would have okay, so decreases the size, and now what does the picture on the right look like? That would just be a border, and that border was created because of the difference in colors here at this edge, right? And so hence this is called an edge filter. And so we get rid of all the like extra information of fills, and you only care about outlines, right? And so in this way, we're again passing a lot less data, and still, as you guys were able to do, you could still identify like a cat based on the outline of the cat, right?
Why does it result in exactly these
So if you, so you can apply this. So let's see here. It's basically the same process as before. So I'm going to do this thing, right, would correspond to here. And then you have a stride of 4, right, because we're going 4 in that direction. And so if you do this math, it will solve out to be these values in the same way that we did with the
Can we
mean.
take the mean before, and then it would be like 10?
Would it? 10 times 1, 10 times 0, 10 times negative
Oh,
1.
now I get it. Yeah.
And then 10 times 1, yeah. So it's a different, we're using a different filter.
Okay, now I get it.
Yeah. Yeah, sorry. So the way, yeah, I guess I didn't explain the actual operation, which is each element is summed, or each element is multiplied, and then you take that average value, right?
It's just the dot product, right?
Uh,
Of the matrix.
Yes,
Yeah.
not the cross product, the dot
Yeah,
product.
it's the
Yes,
dot
yeah,
product.
that's right. It's been a while since I've done linear algebra, but yes. Okay, so you've got different sorts of filters that are going to help reduce the information in different ways. You can apply multiple filters to continuously reduce, right? Because you could do a blurring and an edge, for example, and that would continue to kind of decrease the size of it. So last two, I'll talk about oop. So to sharpen an image, common filter looks something like this. And then the mean blur filter I was kind of using as an example to get us started. There's a more common filter that gets used called the Gaussian blur, which is almost like an inverse of the sharpen effect. And that looks like this. 1, 2, 1, 2, 4, 2, 1, 2, 1. Okay.
Usually 3x3s.
Yeah, yeah. Usually the filters are 3x3s. Yeah. And they tend to be, the process of applying a filter tends to be not so computationally intensive. You're just taking, a bunch of cross products, and you could do that thousands of times, and that compute would happen, instantaneously. Okay. And the context for this is actually these filters are almost like the weights that we had. They are very much akin to being applied in the same way that weights were applied in our neural network, right? And so these are kind of like the coefficients. And in addition to that, we also, analogously with our sort of foundational neural network, can apply activation functions, right? And so so these are our filters. X would be our input, and A is our activation function. And so here, you're kind of allowing the model to decide which filters are kind of most important to help with the classification process, right? And so let's say, hypothetically, that doing a blur of an image doesn't lead to good outcomes in terms of classification, right? And so let's say I blurred a bunch of dog and cat images, and the way that you can think about this is if you guys were to look at those images and you were to have a hard time classifying it as a cat and a dog, right, you could imagine that a neural network might do a similar process where it has many filters at its disposal, one of which would be a blurring filter, and it says, okay, if I blur it too much, then I'm not going to be able to get good classification results, and so maybe I'll use a different filter or try and reduce the importance of like a blurring filter, something like that. Okay? Yeah.
If you're able to blur the image further, couldn't you just reverse it to unblur it?
Yes, you can, and that actually happens sometimes where information in the image gets, let's say you do something like you blur it, find the edges, and then sharpen the edges, something like that. So yes, you can do. There are processes in these neural networks that will both blur and sharpen images, but it's trying to do it in the way that essentially leads you to getting the best classification results as possible. So we talked about ReLU last time, and so this is kind of the go-to, right? This helps with computation of the gradient. Okay. The next step is pooling. So 1, 3, 2, 1, 2, 9, 1, 1, 1, 3, 2, 3, 5, 6, 1, 2. Okay, so pooling is one of the latter steps of the convolution to further reduce the size. Oftentimes you still have more information than is needed, and the pooling can help reduce that quite a lot. And it depends on a couple of parameters. So you have your filter size, the stride, and max or average pooling. So this one has a stride of 2, so it's applying them, applies a filter, takes 2 steps over, applies it. And this particular one is using what's called max pooling. So I'm gonna do something like this. Okay, so can anyone explain what's going on here?
I think it finds the maximum of each of these grids.
Yeah. Yeah, exactly. So this is known as max pooling. So in the red box here, in our 2x2, we're gonna have the max value within there, which is 9. And then in the blue 2x2, the max value of that is 2, and so on and so forth. Okay? So this is kind of the last filter that typically gets applied to your image, sort of processing. It's the pooling step. Okay? Yeah.
So do you always filter then pool, or do you sometimes only filter, only pool? Are these options, or are they like steps in the process?
I would describe them more as steps in a process. You can actually think of these as like, oftentimes these are the layers in your network. And so in one layer you might have a bunch of filters being applied, and then in the next layer you might have the pooling happening. Yeah. Okay, and then the final step is called flattening, and this converts last convolutional layer into a one-dimensional neural network layer. So there's this question of like, why wouldn't we just fully connect So why not fully connect all the layers? Right, and so one way you can think about this is that each one of these filters could be connected. Instead of in these step layers, you could have one large network that connects everything to everything. But the number of weights grows exponentially. And you will have too many parameters to be sort of feasible for computation. So to demonstrate this, consider a 32 by 32 pixel image with RGB channels. Let's say you have a convolution layer with 5 filters, 1 stride. And then you have a pooling layer, 2 filters. Let's say you do both the max and the average, and those are 2 stride. So just the first input and first convolution layer would have, right, and just as a, for context, like a 32 by 32 pixel image is like quite small, right? This is an image that would be kind of like a small thumbnail, right? So we're talking about a fairly small picture here. So the input has 32 by 32 times 3, right, for each channel. Times 28 by 28 times 6. Okay, so the 28 comes from the stride, right? When you do a stride of 1, you reduce the overall image size by 1 in each edge, right? So you reduce left, right, top, bottom. So you go from 32 by 32 down to 28 by 28. And so we have our 5 filters plus input. So this is going to be approximately 14.5 million. Just in the first input and first convolution layer. Nodes. So we want to apply these in a way to help reduce instead of doing a sort of fully connected set of layers. So this will end up looking something like this. So we'll have our 32 by 32 by 3 input layer. 5F1S. So this will be a little bit smaller, 30 by 30 by 5. First convolution layer plus our activation function. Then we go to filter, to stride for our pooling. So this will be 15 by 15 by 10 in our first pooling layer. Okay, and then at the end we do this. We do a flattening, which basically reduces the 3D to a 2D. So you're basically taking all of the matrices and kind of lining it up. So we end up with something dimensionally that looks like this. You have a bunch of nodes in a layer, so you end up with about 400 nodes, reducing down to on the order of like 100 nodes. And each one will be connected, right? And so you have still a pretty well-connected network. And this goes to our final node, which we usually, CNNs use something called softmax, which is a generalization of our logistic function, right? And so here there was a question about whether or not it has to be classification. Not necessarily, right? This particular function solves for, a classification type problem, but it doesn't have to be softmax. So, yeah, this isn't something you necessarily need to know, but for your reference, this is a generalization of our logistic function. So it'll give us probabilities of each of our outcomes. Okay. Oop. Yeah, so this process, it's hopefully a little bit less black boxy. Essentially, the idea is the way that neural networks process images is by going through these series of filters to kind of reduce them in size and to sort of intelligently figure out what are the best processing filters that will let me do the classification as best as possible, and then you can train on that. Once it's identified that, you can take that machinery and feed other images into it and see if I do the same steps of like edging, blurring, averaging, maxing, right, all of this stuff. If I apply that in the same way that I did in my training to get me to the best possible way of classifying the images, then presumably I should be able to do that to any set of images and be able to make predictions on classification of images. Okay. So that's the sort of high-level concept of how the CNN works. And any questions? And then we'll do an example in R. Yes.
How did you go from 400 nodes to 100? Is that just more filtering?
Yeah, so
Or just like when you do the pooling stuff, R automatically does that?
Yeah, so the reduction down to 400, once you've reduced it in the last pooling layer, how do you get to the 100? Well, each consecutive set of pooling things will reduce the dimensions, and then I believe the flattening is just the in any single layer, it'll just be the sum of all of the number of nodes that you have. So the last pooling would reduce it by an order of like 4 or something. Yeah. This is kind of a generic example of a reduction. You could get more specific with the numbers if you were to decide on a particular pooling that had a certain filter size and a certain stride size, and you could do the math to figure out how much that reduces the number of nodes. Yeah, in this case, I just arbitrarily picked something that was like a 4x reduction.
Now, when you're selecting the filters, is it like, let's say for your example, you had 5 filters, 1 stride?
Yep.
Is the 5 filters the same filter? Different time?
No, you usually it's like a combination of common filters. Yeah. Okay. I will say that it's perfectly feasible to do this in R, but actually, if you're gonna do a lot of neural network machine learning stuff, it might be a little bit easier in Python. So the development base for a lot of this stuff is built out, was initially built out a lot more in Python. When I was first trying to do some of this in R, it was a lot harder to do, but it's been built out a lot better now. So, maybe my advice is a little bit outdated. But TensorFlow and Keras are like quintessential libraries for doing this stuff, and it's actually built on a Python backend. So actually, here you actually need you need some of that Python backend to actually be able to run some of this stuff. Yeah, TensorFlow and Keras are both Python packages fundamentally. Yeah, so here I actually am not trying to do this thing for you guys to follow along. This is kind of just like more of a demo for us to look at. So here are a set of images that we're going to do classification on. 1 second here. And so these images, these are actually 32 by 32 images, pixels, right? So just to give you a sense of how low resolution these pictures are that we can do classification on. So the things that we can do, okay, your categories are airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. Okay. So can you guys, are you guys able to tell what these things are? Does anyone, the first one, for example? What was that? A frog. Yes, that's a frog. And then you've got a car, deer, truck, deer, frog, truck, bird, yeah, and so on, right? And so you guys are able to do this classification, and so let's see how well. Yeah, let's see how well this does. Okay. Okay, and so now it is training on our model. And let's see here. Yeah, so this one is going to do the standard ReLU activation function, softmax. Yeah, it has some. So as it's going through the sort of training process, it's going to tell us about the loss score, which is essentially a metric similar to what we've been talking about, a metric to tell you how well the predictions are doing, and the accuracy of the predictions, right? And so it's getting, as it trains more and more, it goes from 40% right up to 65% right. We'll see. This is a lot slower than usual, but hopefully you can see, right, even for a small number of pretty small images on, a modern day laptop, even then it does take a little bit of time to do all this training correctly. And by the end, you're getting some accuracy of like, 75-ish%, right? So it is able to successfully classify. This is just the same plot as before. Yeah. So when I do, when I take that model and I apply it to a set of images that are meant for testing, right, out of sample, it's getting 65% of them correct. So let's see. Yeah. So that's it. Sorry, there's nothing really sort of flashy there, but yeah.
When you say it's getting it 65% correct, what do you mean? Getting correct, like whether or not it's a bird, frog,
Yeah.
horse?
Yeah. So there will be an image. There's an image with a classification associated with it, and so it might be a picture of a horse, and then it'll say this is a horse, right? And then the model will be like, well, I think that 60% of the time it's a horse, and 40% of the time it's like a frog, right?
It's not looking at all of the images in one image?
It's looking at a different set of images so in this particular part of it, I'm in the same way that we talk about training the model, right? Yeah. So we've trained the model on a particular set of images, and then, similar to the way that we might train the model to get parameters on some set of data, and then we take a testing set of data, we pass it into the model that has those now trained parameter values to see how well it predicts on giving us certain outcomes, right? And so it's the same thing here. We give it a different set of images and see how well it does on classifying images that it hadn't trained on, and it ends up with this accuracy. Yeah. Okay. Any other questions? Yeah.
In the plots, for example, here, first the accuracy is low, but then it increases for the validation. But at some for example, at epoch 5, it stays the same?
Yep. Yeah. So the training and the validation, right? You can think of that as like kind of like overfitting, right? The idea is I can continue to improve the model, feed more data, make the model more complex, but that doesn't necessarily give you better predictive outcomes, right? And so when you are using metrics like accuracy or loss, specifically for the training set, remember that in that case, we're only decreasing bias, but we don't know much about the sort of variance part of the error until you do the testing data. And when you do that, it's like the model actually at some point, doing all this stuff doesn't actually improve the predictive outcome. Make sense? Yeah.
What does the loss refer to then?
Loss is, so I don't know, I actually don't know how they do the calculation for loss, but it's going to be based off of essentially how wrong the prediction is. So it may have to do with the probabilistic outcomes and how they differ from your true measurements. And so I believe, well, it'll be some version of a inverse of your accuracy, but I actually don't know exactly how that's measured. Any other questions? Okay, and so, the technique in itself, it is what it is, but a lot of it's built off of the same foundational concepts that we've been talking about, right, with the training versus testing, and then this idea of like overfitting and how that plays a role in kind of the bias component of the error versus the variation component of the error. Okay, so this is a good spot. We'll take a quick break and then we'll do a sort of wrap up of our class. Okay. Hey, what's up?
Just a quick check-in. So we finished with data pre-processing,
Okay.
onto analysis. We decided on GAM.
Okay.
And I just want to make sure that, for a comprehensive analysis, do we have to choose more than one approach, or do you think GAM and talking about the different models we get would be enough?
Yeah. So I would say it's probably good to have more than one approach, but you don't need to show all of it for the presentation.
Yeah.
But it would make sense, right? Obviously, in the report that you would have all that stuff.
Okay.
Yeah.
So something, because a lot of us have like coinciding deadlines, what we're probably going to do is show our GAN and then say we will do an analysis of these alternative approaches.
Sure.
Would that be okay?
Yeah.
Okay.
Yeah.
Just want to make sure. Thank you.
Mm-hmm. All right, let's get back to it. So, actually, do I even talk about that here? Really, a lot of the class kind of boils down to this idea of, we've got a bunch of data, right? X1, X2, X3, and so on. And this is question of what to do with it, right? And I'll just quickly say that, most of the time we have Y, and in the cases where we don't, that is called unsupervised learning. Oop. And that is all the clustering techniques that we talked about. It's not only clustering for unsupervised, but usually that's what people are referring to when we talk about unsupervised learning. But the rest of this is all going to be supervised learning. And the two kind of big ways we think about this are so regression versus classification, which really is still regression at the end of the day. But, we have all this lingo that people talk about, right? And so really what we're talking about here is continuous response variable. So this is our Y versus discrete response variable. Okay? So let's focus in and think specifically about regression first. We have our linear approaches, and then our sort of more nonlinear approaches. So we start off the class thinking about our sort of most fundamental linear regression, something like this. And so at this point, hopefully you guys are all familiar with, what does beta mean? And what is epsilon, or our error? And part of what we talk about is the the model diagnostics, right? And so everyone knows how to do these linear regressions, and there's this question of, well, how do you know that they're sort of any good, right? And so I think even prior to the class, a lot of folks were familiar with some of the traditional ways that we think about them, right? Like standard errors and R squared. So traditional considerations. Standard error, R squared. But we talked about a whole bunch of other metrics that you might want to think about as well. Also, my reminder back to always check your residuals. Right, and so as we talked about, if your residuals are randomly dispersed about 0, that's good. But if you see patterns in your residuals, that's bad. But going back to this thing, if I've got y equals beta 1 x plus beta 0 plus this versus a different model, let's say alpha 1, let's say x2 plus alpha 0. Let me get rid of this. So how do I know which of these models is better? What are some things that I might want to think about? And maybe I wouldn't say better, but what sort of metrics may help me investigate different sort of aspects of the model? Right, so we talked about, you know, your R squared and your standard error might be points of comparison. What are some other things that we talked about? Yeah, MSE. Oop. So mean squared error is the big one, right? So you make a model that predicts an outcome, and so you might want to care about the thing that gives you kind of the best predictions, right? So MSE is the one that I kind of harp on a lot. There's some other metrics that we discussed, AIC, BIC, things like that could be used for comparison as well. And typically those are in the context of like selection. Okay, and then we talked about, right, if there's really one thing to really take away from this class is the errors in your bias. Bias versus variance, right? And so if my pen would work. Oh, maybe it's frozen. All right. Oh. Whoa, okay, hang on. Okay. If there's like one thing to really take away from this class, it is this concept, right? So error. So our total error is the sum of the bias, which decreases with model complexity, versus our variance, which will increase with model complexity, right? And so it is this balance between getting your model to reduce the bias as much as possible without overfitting, right? And so we wanna aim for the here. This is our sweet spot. And the kind of classic way that we go about getting there is through cross-validation, right? And so cross-validation lets us do this training and testing based off of some set of data to try and get to that sweet spot as often as possible. And we've seen so many examples throughout class of different ways of that models try and do this. Okay, and that concept helps us do things like subset selection, right? So there's a question of how do we choose variables for a model or identify important ones. Right, and so the ways that we can do that, stepwise selection. We can do shrinkage approaches. Right, so stepwise selection, you've got our forward and backward stepwise selection. Shrinkage, we have our ridge, lasso, and elastic net. We didn't actually cover this in class. There's also something called dimension reduction. So if you've ever heard of something like a principal components analysis, that is a sort of slightly different way of thinking about this, where you're trying to extract the most important components of each of your variables. But in principle, all of these approaches are trying to essentially do the same thing, which is you've got a bunch of variables, right? And it's like, how do I take all of these variables and extract what is important about them into the model, right? And so if you've got a huge data set where you've got 100, 1,000, 10,000 variables, these approaches are all meant to take that information and try and create the best model that it can out of all of that, right? And it does so in very different ways, different approaches, but that's kind of the fundamental idea. Okay? Any questions? Okay. And then from here, we do our sort of evolution from linear to nonlinear, right? And we talked about all of these different approaches. So polynomial regression, piecewise regression, into splines, smoothing splines, and kernels. And maybe I'll put a little parentheses for our GAM here as well. And then even our neural networks, right? So I think that about covers most of what we talked about with continuous regressions. And then we had this whole other class of stuff under classification. And here we have our logistic regression, our LDA, and then to the more, so if I say parametric, and then we have like more semi-parametric stuff, and then non-parametric down here. You know, we've got our support vector machines all the way down to our k nearest neighbors. Yeah, and so we have these tool sets that we have built up, right? And so in our continuous space, we go from linear all the way down to neural networks through this pathway of like going from the most parametric models to semi-parametric, non-parametric. And that's gonna enable us to think about doing regressions in different sort of contexts, right? And the main distinguishing context that I really tried to emphasize in this class, right, is on prediction versus inference. And you know, one way you can think about this in addition to what I've been talking about is kind of parametric versus non-parametric, where this is more on, oh, sorry, other way around. Non-parametric versus parametric. Oop. Right, because we care about interpretability versus here we care about predicting outcomes. And so you may not care so much about the relationship between variables on the more predictive side of things, and therefore this idea of generating interpretable coefficients is less important. And this is kind of where I might be more interested in getting into like the machine learning stuff and neural networks, where the weights that might correspond to a model that's trained in a neural network aren't going to be very interpretable in any sort of sense that we're kind of used to, right? Whereas in inference, if I stay, let's say, in my sort of linear regression space, you know, those slopes and coefficients help me to understand relationships between variables in a more direct way, right? And that gets us to this whole subclass of problems about causality and identification. And here we talked about causal diagrams to help us think about how to structure our models and to inform us on what tools that we might be able to use. And we talked about things like fixed effects, differences in differences, diff and diff, and instrumental variables, or instrumental variable regression, right? And so these are all specific approaches that I would say are firmly kind of nestled in this idea of wanting to do inference, and more specifically about thinking about causality. Yeah, and so, you know, are very stereotypically, you know, you have groups I might characterize as like statisticians, machine learning people over here, and then you've got econometricians, social sciences over here, social scientists. And right, this isn't about one way being better or worse than the other, or that one group is being sort of, more advanced or not versus the other, right? This is about contextualizing the problem and trying to use the best approach for what you need to do, okay? And I really hope that one of the things that you guys can take away from this class is that when you start to ask that question of what you want to do with the data, that will then guide you to understanding, or that you will understand the right tools to apply to best answer the questions that you are seeking to answer, right? And so I hope you're not doing like fixed effects, IV regression when you're like focusing on doing some kind of predictive outcome, and I hope you're not, doing some wild machine learning neural network if you're trying to figure out some causal influence of a variable on an outcome. That's going to go very poorly for you. So hopefully that's one kind of big takeaway from this class. Yeah, and so more generally, some things to think about as you do this analysis. Think carefully about what the statistics say and what they don't say, right? I think that's a point that I tried to emphasize at the beginning of the class. The very common misconceptions of like what constitutes a good model versus what a statistic is actually telling you, like an R-squared or a statistical significance, right? Just be mindful that those are useful metrics that describe specific things about your model, but are not these all-encompassing metrics that just tell us how good or bad a model is. Think about the interpretability of things, and I'm not talking about interpretability of like coefficients and variables. It's sort of in general what things that are important that you're extracting out of results of models and what that's telling us, why it's relevant, right? And so really this kind of speaks to this idea that like you want to step away from this thing where I take data, plug it into a model, get results, and that's it, right? You want to really understand and contextualize, what you're doing and what your results are telling you. And then I think the last bit of advice I'll give is also to kind of know your audience. There's times where I see these pretty sophisticated like statistical presentations being made to, a group of people who aren't statisticians, right? And so there's a lot of good work that may go behind the scenes that maybe is not, as celebrated or sort of understood, and that you don't need to necessarily kind of push that on the audience, and vice versa. If you do have an audience that kind of knows their stuff, you want to make sure to show your due diligence, right? And so it's kind of this is less of a applied data analysis skill and more kind of a general one, which is right to design your presentations and papers and reports in a way that that is going to be really coherent to your audience. But I think it's particularly important in this field because there's a lot of ways that you can misrepresent and misinterpret data and models and results. And so part of what we try to do in this class is to give you the training for you guys to talk about all this stuff in the right way. Yeah, and so that's my bits of advice for you guys, and hopefully you guys all learned a little bit of something in this class. And yeah, I hope I will be able to see some of that in our presentations next week. Yeah, so thanks all. And we get to end early today.